about this. And the story to start with is the same story that I told you some weeks ago. Okay, the story is about I have a hard disk or a file which is shareable to the public, right? I create a file. As long as I'm the owner, I can read it, I can write it, and because there is no control over a file access, you can open a file with two processes, name whatever process you want. Okay, maybe one is ls redirect, no, ls start. Okay, ls means open a file. Or maybe you create your own program. Your own program is reading the file. At the same time, another process writing the file. Okay, and it is allowed and no control. Okay, allowed and no control. And now another example that you, how only one guy asked me about a question on assignment 1. Okay, how many of you have started this assignment 1, phase 2? Okay, so you already know it. Okay, so when I talk about the example, then you will know what I'm saying. When you create a pipe, okay, a pipe actually just behaves like a file, right? You can open it, you can read it, you can close it, you can do whatever file-like things, okay? But where do you create that pipe? Before fork or after fork? Before fork or after fork? Before fork, okay? So that means what? That means that pipe is actually create, and then you artificially share it using fork. Artificial, right? Because you control it, okay? And now two processes look at the same set of pipe, and what is more magical is the two processes know how to operate through it with control. This is without any control. Yeah, you can do the write, the read, okay? Now if you're working on the pipe, you can try to reverse something, and he already faced a problem, I/O error, input-output error. Okay, they are control if they're using pipe. So this chapter is, this part is to tell you what are the possible controls, or what are the use case why we need control. One of the control, maybe I tell you what are the problems. Okay, the control itself is not easy to talk about, right? I can tell you control A is like this, control B is like that. But do we have a problem in the first place? Do we have a problem to allow the file to be accessed concurrently with a read with a write? Of course, there will be a problem. Maybe this guy is reading stale data, or we call it out of date data. Okay, maybe two guys are not reading, but both are writing. So who will win? The last guy who writes to a piece of memory will win. Okay, so the problem is like this. We will try to first understand what are the good practice, what are the introductory IPC environment that we have, the pipe. Okay, and the pipe, why it is IPC? Because you will create two different processes. They talk together, but they don't talk together directly, but through something public. Okay, but I would say only public these two guys. Okay, and when you create a pipe, okay. Now this is assignment 1, right? You create a shell, and a shell receive the command line with a pipe. Then you will call the pipe system call, and with this system call, they are shareable to this two process because you do it before fork. Okay? And one system, one process. One process is keep on writing data in. One process is keep on reading data out. If you reverse it, you will get I/O error. Okay, or some even more horrible cases like receive a signal that kill you. Okay, so there are some codes that our TA have talked about. Okay, the dupe, the execute. Okay, now I'm not going to talk about the dupe. I'm talking about something even more important. Okay, the more important thing is what is that pipe? That pipe you need a system call to create it, and when you create, you just receive two file descriptor or two ends. One is write end, one is the end, not ending right. So end for the writing and the end for the reading. Okay, and they are the two ends. And actually, this is a space created inside the kernel. Then you should ask the next questions. What are that data? The data type is actually a queue, a finite queue. How big it is? There is a command to check. The command is called ulimit minus a. Can you find the name pipe? How big it is? 5K, 4K. 5K, stupid. 4K, right? Can you find it? A times 512. Yeah, okay, if you cannot find it, okay. Yeah, here. So this is the limit, and this is the limit within your own shell, okay? You can change it, okay? Then your shell will have a bigger pipe, okay? Now, the problem is not about its size, how big it is, but about it is finite, okay? It is finite space. You never asked to handle this before, right? This is the first time that you see, oh, the queue is finite. So what will happen? The data structure course don't tell you. When you keep enqueuing to a full queue, what should you do? In data structure course, you will call exit 1, right? Yeah, enqueue, oh, full exit 1. Or printf, okay? Kernel won't do this, right? Kernel won't say that, okay, you are ls, you keep enqueuing. Sorry, I run out of space now because you have a producing rate, or we call it arrival rate, stronger or bigger than the consumption rate. The consumption is slow. The producing process is fast. So you make the queue full. What should you do? In their structure course, they will tell you, yeah, printf, queue full, exit 1. Here, won't. You won't find that guy being killed. Never. Never. Okay? Then what should that whole thing survive? Now, this is the whole thing, right? The whole thing still works perfectly. I can show you. Okay? So, give me 2 minutes. I write a program first. Test.c. Wow. So happen I have a get char, great. I just want to use get char. Okay? I'm doing while 1. I pretend that this is the ls.pycat, and this is my cat program. I read things using while 1 fast enough, right? But how about I put a sleep 1 here? Then it's not fast enough, right? It's being very slow. Okay? So to confirm that everything is working, I will do things like this. Okay, so everybody get my idea. I create as if I'm writing a cat program. The cat program, you write a character, then you output a character. So I just echo it using getChar, and after I get the character, put it in putChar. Okay, but originally there should not be any sleep here, right? Shouldn't have sleeps here. Now comment it, compile, make test, ls.pycat. It's work. Right? It's work. Ah, well, ls.pytest. Oh, sorry. I shouldn't be that lazy, huh? Okay. int c equal to get char. If c equal to eof break. Okay. Better, huh? Yeah, okay. Yeah, it works, it works. Now, what I'm doing is to emulate the case that I just said. I want to have the producing rate much, much higher than the consumption rate. Okay? So I put a sleep here. So, this is the consumption rate being very slow. Test. Oh yeah, but I need at least a few seconds. Okay, go ahead. ls.pyt /test. It takes some time. Come on. Ah. Okay, okay. I shouldn't press Control C. Oh. Okay. You sleep. Nanosecond sleep. Better, huh? Mm. Yeah, too fast. You know, this. I should prepare this program. Yeah. Okay. Better. Yeah, see, it works, right? It works. Now, what is the problem? The problem is, it seems that the pipe is very clever. How clever it is? Take a look back here. This guy seems to be not affected by me, right? You bomb data into the pipe. Because it's contain 4Ks only, I think the data may be smaller than 4K. So you work. I give you another challenge. The challenge is this. Then this won't be 4K, right? Still works. Still bombing things out. Okay? So it seems that this area, of course, there's 4K. It's not a joke. Okay? Actually, it's a more than 4K. It becomes 8K. It becomes 16K. No, that's not the case. Okay? The case is it's still 4K, and the enqueue process seems to be not altered, not being stopped. And here it's dequeuing very slow. It seems that some magic happens. Why this guy have a rate control? It seems to be a rate control, right? This guy don't have any rate control because I control his rate. Okay? This guy know that you are slow, so I'm pumping everything slow. It seems not, right? I don't believe the LS is that clever. So who have the rate control implementation? Here. The data structure itself. Or I should say the enqueue call itself. Yeah, when you enqueue it, of course, back to the basics of the data structure course, you find that the queue is full. Now, this time you're not printing an error and exceed 1. What you should do? Suspend it. Suspend this guy. Until when? Until I get some space here. The DQ API will have something different this time. The DQ API find that, originally it was full. So you have a very high chance that this guy is being suspended. I send you a set continue to continue your execution. Okay? So then, now you understand what happened if I reverse the order. This time is the producing rate is very, very big. The consumption rate is very small. How about I reverse it? This guy sucks. Produce many data, but very slow. This guy consume very fast. Then, in order to make this entire data structure or entire execution works, if you dequeue on an empty queue, you are not printing an error, but suspend it. Okay? If this guy keep on producing things, but find that originally it is empty, so what should you do? Send a sitcon to this guy so that this guy continue to run. Okay? So this is some intrinsic idea or intrinsic requirement that a pipe should have. There are something more. What are something more things? How about these 3 guys? Should they run in a parallel? The shell, of course not. The shell should be waiting for them to finish, right? If you start writing the shell, then you know what I'm talking about. Okay? The shell should be suspended because of the wait system call. But how about these 2 guys? Should we allow them to run like this? Okay, I'm a shell, I call fork once, this guy execute, I wait for this call, this LS to terminate, and then, because I'm using for loop, wait finish, fork again, to let the LS run, and then wait for the LS. Should I implement it that way? No. Then what should be the correct way to implement it? At the same time, parallel. So the code should be, you have a for loop, just call for and execute. Of course, some do or some close together, okay? But that shell doing a for loop, I don't know how many pipes you have, okay? But whenever you face this condition, you have to create a pair of process connected with a pipe. Make sure that you run in parallel, because keep in your mind that you will have a chance that this guy producing things which is much more than the buffer here. You will enter the suspension days because you produce too much. You need your partner to wake you up. Okay? If the partner is missing, you didn't create it, sorry, no one can help you. Your entire system will get frozen there. Will not recover. The same thing, same case here. If you only create this guy, the queue itself is empty, so this guy don't have anything consume, suspend. I need the partner find that when you enqueue, you find that the end has nothing, so I wake you up by saying set cork. Okay? So this is the pipe. And this is the intrinsic requirement if we face something finite. Of course, if this becomes infinite, the case will be much simpler. You can think of a case, yeah, what happens if this is infinite? How can we modify the enqueue and dequeue in order to cope with this? Okay? Yeah. So when you look at this so-called FIFO system, we have a name for it. It's not a simple FIFO system or pipe. We call it producer-consumer model. What is producer? What is consumer? The intrinsic idea or intrinsic requirement is we have a finite buffer, and in computer, you know, everything is finite. And what happens, this is not a queue inside the kernel, but you create a file to pretend to be there. Then you have to write your own enqueue, dequeue API. This class or this part is to tell you how to write these APIs. I mean the algorithm. The algorithm in controlling parallel processes. Okay? So this is the start, not the end. Okay? This is the end of the beginning. All right.